Hello, everyone, and welcome to the second installment of the Autodesk Water webinar series, organized by Smart Water Magazine and Autodesk Water. My name is Cristina Novo, and I am Technical Editor at Smart Water Magazine. It's a pleasure to have you join us for this second webinar of the series, where we continue our journey toward reimagining the future of water management through the insights of industry experts who are going to discuss key topics and case studies. From safe supply and sanitation to flood protection to asset maintenance, our agenda will delve into the most current topics in water management. In a world where water-related challenges remain present, our ongoing exploration of innovative and sustainable solutions is vital. Among these solutions, digital technologies stand out as crucial enablers, providing tools for more efficient and effective water management. Autodesk is leading the way in this transformation, offering its expertise in design, construction, and advanced hydrological modeling. As you know, the webinars in this series are open to all and free to attend, offering a unique platform to engage with our experts directly. Stay tuned for future announcements with the dates and topics of more webinars in this series. And now let's dive right into today's webinar, Forecasting Floods, Protecting Lives. As climate change intensifies the frequency and severity of extreme weather events, investing in robust flood forecasting and early warning systems becomes imperative in order to minimize risks to communities and infrastructure. This is an utmost priority across the world. Just yesterday, we heard the devastating news of floods in Kenya causing the lives of more than 70 people. In this webinar, we're going to hear about Türkiye's approach to flood risk management through its flood forecast and early warning system. We will hear how the system works, the use of InfoWorks ICM and ICM Live for modeling and simulations, and we'll also see a simulation of the web interface. You can ask questions throughout the webinar using the chat window in Zoom. Please identify yourself and your organization when you ask the question. You're also going to see on your screen some poll questions throughout the webinar. The webinar should last about 1 hour in total. And now I would like to introduce the three speakers of today's session. The first one will be Özguray Aydin, a hydrogeological engineer with over 18 years of expertise in water projects. He has been the Water Solutions Manager at Universal Software for the past 5 years. Özguray's involvement in crafting specialized systems that merge technology and engineering has been instrumental in advancing water management practices. The next speaker will be Salih Babagiray. A civil engineer and MSc, he's currently pursuing his PhD studies in hydrological modeling while working as a control engineer at the Flood Forecast and Early Warning Center in Türkiye, under the Ministry of Agriculture and Forestry. He has worked extensively on flood analysis and is part of the team that established the National Flood Forecast and Early Warning Center. Finally, Ziad Aziz will be the third presenter. A civil engineer, MSc, and PhD candidate, he also works at the Flood Forecast and Early Warning Center in Türkiye as control engineer. Ziad is a dedicated water enthusiast who brings with him experience in water resources and its isotopes. Welcome to all three of you, and I would like to pass the floor to Özguray Aydin.
Thank you very much for your kind introduction, and I will talk about why we need flood forecast and early warning system and discuss these topics a little bit in details. As we have experienced several in recent times, the frequency and intensity of floods are increasing, as you said, due to climate change. Now, you see is a heatograph. We called it heatograph, which shows the change in rainfall intensity over time. These heatographs represent the last 8 years from my hometown, Antalya, Turkey. When you examine the data from your location or any location, you will likely see a similar trend and rainfall anomalies as well. Simply, our location has a tolerance limit affected by various factors. When rainfall exceeds these limits, we experience flooding. The authorities develop and implement structural projects to increase our tolerance limits. It's possible to take various levels of measures depending on the region situation and financial strength. Here, I have shown two different levels of measures. Even the first level requires a significant investment, while the higher level measures require larger investments. And one more thing we should be sure about is that even with very high investments, we have a limit, and the probability of exceeding this limit is increasing day by day. Therefore, it's also necessary to manage the parts where these limits are exceeded. In fact, we need to acknowledge that all flood prevention structures have their limits, and they are significantly insufficient for serious catastrophic events. Almost everywhere around the world, particularly in recent time, we are facing numerous disasters where prevention seems almost impossible to given the current condition. Here, our most important ally is the flood forecasting and early warning systems. I would like to focus on basic and general engineering methodology. I can say that we track the natural conditions during the flood forecasting stage. Here, we employ a three-step calculation methodology. Firstly, we adapt rainfall forecast to our model, meaning we integrate current and future rainfall into our platform in the most optimal way. Second, we use hydrological models to calculate the discharge resulting from the rainfall. In short, we establish the rainfall runoff relationship with hydrological models. Third and finally, we utilize hydrodynamic models to understand the impact of the calculated discharge on the region, watershed, river, or city. We use all these stages in the flood prediction system to forecast the location, timing, and impact of the potential floods, including water depth and velocity in the region as accurately as possible. In my final slide, I would like to discuss software architecture and the fundamental workflow. First, we need to prepare and calibrate the hydrological models. In this regard, InfoWorks ICM offers so many alternatives and opportunities. Subsequently, we continuously run our hydrological models with rainfall forecast. Again, here we have the ICM Live application, which provides these tasks automatically and robustly. I would like to emphasize that my personal expectation from systems after error-free configuration, the systems must work flawlessly and continuously. With ICM Live, we have been able to run more than 500 hydrological models with 3 different weather forecasts every hour for nearly 2 years without a single error. I would like to extend my gratitude to the entire development team responsible for this perfection, such a live system. They have truly done an outstanding job in my point of view. This system operates continuously and automatically. It may take a day of almost the entire year. However, when it detects any out-of-limit situation, it promptly alerts all the relevant parties. And here, the early warning system and its operations begin to comprehensive disaster management process. The critical point here is that our disaster management solution has been designed to be in accordance with the culture, social structure, governmental organization of the region. For example, in TATUS, we developed tighter cut application that meets our responsible organization needs in Turkey. When implementing this project in another country or city, especially the early warning part, it needs to be designed according to the region data, available resource, and governmental organization, etc. I don't want to tell too much on TATUS because our country's important experts and my dear friends will provide you detailed insights about it. However, I can say we can develop an advanced engineering platform that continuously collects, analyzes, and correlates thousands of data points from the field, various institution and system. And I can say I'm proud to be part of the team that made this project a reality over an extensive period of time for research and software development. And Christina, I will pass the floor back to you. Thank you.
Thank you. And now we'll go on with the presentation of Salih Babagiray, Control Engineer at the National Flood Forecast and Early Warning Center in Turkey.
Thank you so much, Özgüray, for the nice beginning. Today, I will present an important subject which will be understood more and more in coming days because of the climate change. And this is Salih Salih Babagiray, and I'm a civil engineer. And I'm working at Flood Forecasting and Early Warning Center in Türkiye. I will give some key information about the flood forecasting, and then I would like to talk about our center. We say TATUM in Turkish. It's like a shortening. And finally, I will talk about the TATUS fifth system flood early warning system in Turkey. Yeah, there are lots of floods occur in Turkey. Approximately 125 floods occur annually. And you are watching a short video, the left side, from Kastamonu, the last big event. Kastamonu city is the part of the north part of the Turkey, and 72 people died because of the flood. I'd like to wait a little bit more, and you can see the overflow of the river and the peak time. Yep, let's continue. Yeah, United Nations also support this system because we can prepare some system to forecast the floods thanks to developing technology, and they post some announcement and some information on their social media. And what is flood forecasting? Yeah, there are three components here. First of all, meteorological forecasting. And second one is hydrological forecasting. And finally, hydrodynamic analysis. And after that, if we say something about for all these components, yeah, we can prepare a flood warning to warn to the public. Let's focus the meteorology. Yeah, precipitation is the most important thing for the flood forecasting because most floods occur because of this heavy rain, and precipitation should predict before it's occur. And these informations are so important, like location, date, duration, intensity, and type. Second one is hydrology. The hydrology, yeah, we should prepare some hydrological model because we need to forecast the peak flow and lag time. And finally, yeah, after talking about these forecasting, yeah, we should say something about the river bed and river overflow, and also flood maps. TATUM is a center in Turkey, flood forecasting and early warning center, and we have established in 6 years ago. And the main purpose is flood forecasting before 12 hours ago, at least. And there are three general directorates here. There are some experts comes from these general directorates. First of all, General Directorate of State Hydraulic Works, we say DSI in Turkish, so think again. And they are responsible for flood control and hydrology also. And second one is meteorology. Yes, they are responsible. For the meteorological forecasting. And finally, General Directorate of State Hydraulic Works. And we collaborate with Disaster and Emergency Management Presidency because they are responsible for warning to the public after these all studies. And let's pass the TATUS fifth system in Turkey, flood early warning system. And I would like to talk about setups and abilities, our system. And yeah, the data is the most important thing for the flood forecasting. We need lots of data like meteorological, hydrological data, and then data, and also flood maps too. And we have collect all this data before started to analyze. And we have prepared 15 hydrological. We have focused on the 15 basin in Turkey, like a pilot project, and more than 100 hydrologic model has been prepared and calibrated too. And we use both ICM. We use ICM, both hydrological model and hydrodynamic model. And the system can prepare hydrological modeling when you want, where you want, because if you have the data, yeah, you can prepare hydrological model easily. And hydrodynamic model, yeah, we use also ICM for hydrodynamic model, and there's a good thing here, and the ICM can prepare the flood maps real time, and there are two options to use the flood maps. Yeah, you can use real time and the catalog. Yeah, we have also catalog in Turkey for the a lot of place in critical area, and you can watch the video the right path and the inundation situation for these places. And the system can, in the system, we can create lots of warnings, like points warnings, atmospheric weather observation system on stream gauging systems or forecasting points we have choose. And other one is integrated warning. Yeah, you can select more than one points to create warning. And the last one is, yeah, there are lots of options to create warnings like dams, stream gauging systems, or AWOS. My colleague Cihat will talk about more. And the web interface is important. Yeah, we should operate the system via the interface. So there are lots of layers like numerical weather forecasting models. We use 3 of them: ECMWF, Aladdin, and WRF. And also there are some layers comes from DSI, like system gauging systems, and there are lots of flood maps for the layer or all the loss of placement. And finally, yeah, if we do lots of things about the hydrology and hydrodynamic modeling, and we can say something about the flood will occur or not, and there are some threshold here, like Q100, Q500, or critical cross-section started the flood. And yeah, we are doing all studies for the reports, flood forecasting reports, and the report should include the feature of information. I mean the basin, for the basin, and precipitation, flow, and flood information like location, date, duration, and effects. And we are preparing the report and sent to the AFAD emergency presidency and they warn to the public thanks to reports. And finally, yeah, there are 3 components: meteorology, hydrology, and hydrodynamic forecasting. And both system and also our experts, our colleagues, analyze the warnings and prepare a report for the basin to send to AFAD, and AFAD warn the public. And our main target is we are trying to expand the system all over the Türkiye. And thank you so much. I will give the floor to my colleague Cihat now.
Thank you, Salih, and it feels great to be here today. So far, my colleagues Salih and Özgüray showed what's been done in the kitchen, and I will show you how it displayed like on the table. And here it comes to our TATUS web interface, and here every user will have their own unique username and the password. Right now, the only people can access here this system working in this team. And as a second phase, because still the system is still under the construction, and after running some tests, we will give the permission as a second user for some relevant authorities, as a third user to the public, and every citizen can access this web interface. And when you have your username and the password, you can enter our web interface. And this page welcomes you here, and you can change this welcoming page in the GIS server. And this is a pretty user-friendly system. If you save your settings, and you will see the next time when you open the web interface as well. And in our web page, we will have the different data and the different layer, and these layers can be changeable also in GIS server. And we can see here as the alarm points and automated weather observation stations. We call it OMGI, and stream gauge data and other water level data in different structures. And we can show the boundary layer as a province, and maybe our pilot project basins, and the second phase of the project boundaries. And if you click here, the automated weather observation stations, we can see this triangle shape, and these present the precipitation data comes from Turkish State Meteorological Service. And here, also, if you click one of the points, automated weather observation stations point, you will see its attributes, and you can add and subtract and add these attributes like in GIS server as well. If you click the graph, and you will see this hydrograph is plotted in date to versus date versus millimeter per hour. And you can expand or see the specific date as you like to. And here, for the graph, you can extract this graph is in the different data, different type, file type. You can as PNG as an image, a PDF or CSV, other type as well. And here, in our system, as my friend Salih said, we have some forecasting point in 15 sub-basins here. If you click one of the points, green dots, hollow green dots, and you will see the different layers, different line, and it's all represented numerical weather forecast. Here, we don't have the measured data because there is pretty small flow on the river. That's why it's not measured by the stream gauge stations. And each numerical weather forecast creates a different water volume, flow volume. And if you move your cursor, and you will see how it's changing over the graph. And if you click specifically in line, and you will see individually, and it can be exported in a different data type as well. And here we can see different, as I say, numerical weather forecasts, and with radar as well. When you click one of them, for example, ECM WF for 24 hours run, and you will see the pixel on the Türkiye's map. But right now, on that day, specific date, there was not much rainfall like in Türkiye, but you will see like the left corner of the screen, some small squares to show the rainfall. For example, here is a 1.38 millimeter rainfall, yeah. and you can see the details on the bottom corner. If you click the radar as well, you will have the precipitation values. But that time, sky was pretty clear. There is some small events you can be seen, like in the Black Sea and some part of the Turkey as well. Yeah, if you click one of the pixel here, you will have some precipitation data. And one of the good abilities of the system, you can manage data easily, and we use stored query language SQL. And if you need some specific data or the specific date, and you will just search using the SQL, and you can create as many as you like and get the data in the Excel file, and you can manipulate your data in the different software or Excel file as well. And here we have the specific stream gauge number, D22A082. And we'll say like top 100 flows of the specific stations and ordered by the flow. And when we run this, and we will have extracted Excel file. And this is the good part, one of the good parts, and we can create an alarm, the manual alarm, and you can put a name and put some certain time, start date, end date, and if you want to get an email, you can type your email, and when the alarm is triggered, you will get an email in your inbox, and which layer you want to use to create an alarm, as we say, like TATUS or stream gauge stations or some other stations responsible by the different institution. And here, if you create an alarm, you will have the alarm list, and you will say the people's alarm as well to see if it's created before, or you can recreate it again. This is one of the example here. If you update this alarm, you can give it a name, and you can type some email, and as I say, the notification can be sent different the mail address, and add a description. This is the good part, and we use flood risk management plans, the thresholds here. If you say the stream gauge measure like 1,148 cubic meter per second, please send an alarm. And this is the most critical one, and we this is the color coded, and we put the red color, and these are the levels as well. And when you click specifically, you can change it. And if you want to change the color, you don't need to go again and type everything at the beginning. You can just change in the symbology in the drop-down menu. Is pretty user-friendly. Yeah, and when the alarm is triggered, you will see one ringing bell on the screen, and says, yeah, something is happening. And when you click the bell, and you will see this alarm is triggered, and what time is triggered, and which threshold you give, and what's measured like on the field right now. And if you click show me on the map, and it directly goes to this point. And this is one of the points, the forecasting points in the Black Sea region. These are the most rainiest places, taking the most rainfall in a year. These are the places we work on in the pilot project, and we will expand in the second phase. When you click the point, and you will see the different image. These are all prepared in flood risk management plans. And when you click this one, you will see like 500 years flood. and you can extract these data or put into your report and change a bit if you like. And yeah, it also show the risk and color coded as well, and most vulnerable places can be seen like on the map. These are one of the greatest ability is a 3D view, and you can see image as a 3D if you move your cursor, and you will see how the topography can be seen like over the web interface. And if you move it, and you will see the settlements and how rivers shape, and you can manage how it's seen. And if you click the river net here, you can follow and where can be started, and you can just start thinking, and helps you to decide which point can be the critical and over the system. And we can also see the inundation map as a 3D in ICM. Yeah, if you turn it into 2D again, and you will see how it's look as an overview. And as we say, forecasting for lives, protecting lives.
Thank you. Thank you very much to the three of you. We have heard from Özgüray Aydin, Water Solutions Manager at Universal Software, who has introduced flood forecasting for us, and emphasizing that that early warning part needs to be designed according to the region, to the available resources, to the available data, and to the governmental organizations involved. We have then heard from Salih Babagiray, Control Engineer at the National Flood Forecast and Early Warning Center in Turkey, where he has introduced us the main points of TATUS. That's the acronym for the National Flood Forecast and Early Warning Center, emphasizing the importance of data for flood forecasting. So both meteorological data and flood maps, and the use of technology. And finally, that very interesting demonstration by our third presenter, Ziad Aziz, where we have seen the web interface with all its functionalities, including the creation of those alarms where we can specify thresholds in the data, where we can specify the details of the notifications, and where we can see the locations in 3D thanks to ICM Live. Thank you again. And now we're going to have our question period. So I would like our audience to please use the chat window in Zoom to send your questions. And also I would like to, just in case you're not aware, Zoom has a subtitling function. So at the bottom of your screen, you can allow those subtitles in different languages if you are interested in that. Thank you. Hello again. We're going to start now with our questions. And I would like to start with a question that has arrived for Özgüray Aydin. In your presentation, you have mentioned dozens of live data integration. What can be said about the lack of data or the interruption of data communication in this system?
Yes, thank you, Christina. In TATUS, this system collecting over maybe 10,000 data points hourly from the field. I'm talking about maybe thousands of meteorological stations, thousands of stream flow observation stations, hundreds of dams and snow measurements, lake observation, and many more data source that I might be forgetting at the moment. By the way, all of this comes from the different system, different institutions. Essentially, what we are offering as a powerful solution is to gather all measurements related to the flooding in one place, keep them analyzable, and make the most accurate predictions possible, or rather maybe make the best possible prediction with the available data. Therefore, in pre-disaster times, we focus on data at hand to come up with solutions. In post-disaster evaluations, especially TATUS, of course, provides suggestions for improvements, new measurements, locations, and types, considering the questions of what could have been done better.
Thank you. Thank you, Özgüray. We have quite a few questions, so we're going to keep moving on to the next one. We have a question for Salih Babagiray, and it is, can you tell us a little bit about the calibration process? And also the same person would ask if you had a chance to test your forecasts.
Thank you. Yeah, the calibration is the most important issue of the hydrological modeling, where you calibrated to the basins, all basins, on even base here, not continuously. We set an appropriate threshold for each basin with at least 10 events, peak flow, I mean, and calibrated to the model manually on these peak flows. Yeah, we had only one time chance to test the system. There was a homogeneous precipitation, and we have predicted the flow resulting from this rain, and the accuracy was over 80%. However, yeah, we don't know yet its accuracy to the local and southern rains, and yeah, we are waiting for this. Thank you.
Thank you, Salih. Yes, I'm sure we will be hearing soon more about the next steps in your testing. Now we're gonna go with another question. This one is for Sihat Aziz. In your presentation, you've talked quite a bit about the alarms. There's a question specific about them. So it asks, what is the complex alarm mechanism and what exactly are the advantages of this mechanism?
Yeah, the complex alarm mechanism is creating the complex structure to see the specific locations. If you put an alarm using the layer called like stream gauge, and if you say the stream gauge, if stream gauge measures like more than 1000 cubic meter per second, and you can add more, and at the same time you can use automated weather observation stations. As I can say, like if you put like more than 50 millimeter per hour for the rainfall, you can combine these two and say, okay, if this happening and I have another parameter, like another threshold, and you can give me alarm after these events happens. These two combine, or you can maybe add 3 or 4, but if you add more, it's getting like the more less illogical. 2 can be is like more logical, like with stream gauge and automated weather observation stations. And you will have the complex alarm to see if the event is continuous, or you want to see how can be dangerous, or you can manage in the meantime.
Okay, thank you. Thank you, Zihat. We have another question dealing with the specific of the data. So it's from Miriam Lopez Lineros, a hydraulic engineer for smart water software at Schneider Electric. And her question is, well, she would like to know how the system maps the information from rain gauges and radar. I don't know who might want to take this question.
I can answer, and we can use this different data sets from the different institutions. Some institutions are responsible for hydrology, as my friend said, and hydrometeorological event is run by Turkish State Meteorological Service. They produce data, and they are responsible for the stream gauge observation stations, weather observation stations. And state hydraulic works are responsible for stream gauge, water level like in the dam or a lake, some other reservoir. And we have these data from the different servers, and we combine and put into the system to represent as a whole in a one particular software or web page.
Okay, thank you very much. Now, let's move to one about the specifics of the technology. It's addressed to Özgüray Aydin, and it's from Billy Busumusi Takwala from South Africa. And the question is, how is artificial intelligence viewed in your technology designs?
I can answer it personally. That's my personal view. I think for the flood forecast system, maybe we use the hydrological and hydrodynamic models for the physical modeling, and at least 10 years more. Artificial intelligence is could be very good for the if you have a trend and normalization, but in flood, we are generally talking about the anomalies, very different anomalies. And it is hard to especially expect the floods before it occurs. Because of it, we always say that every flood is different. If you don't have a trend and if you don't have a normalized values, it is very hard to make it just with a machine or just with AI. Because of it, we are producing very good forecasting tools, and most important things, the forecaster. We are just developing tools for forecaster. This is a very comprehensive tool, but at least at the end of the game, the one specialist in the area and also in the topic could decide about the comprehensive disaster management rules. And I think maybe 5 or 10 years after from now, AI could be integrated for the forecasting. But in the meteorological side, when we talk about the meteorological forecast, absolutely AI is so useful for the meteorological forecast. And maybe with the better meteorological forecast with AI adaptation would be make us the more powerful for our flood forecast. But flood forecast side, in my personal view, could be physical model based in next 5 or 10 years maybe. Thank you.
Thank you. Thank you very much, Özgüray. Now, let's go again to some questions specific about the system, in this case, about the resolution. So this question is from Mohamed Egorab from TU Dresden in Germany. And the question is about the spatial temporal resolution of the rainfall forecast, and also if downscaling methods are used. anybody would like to try to
Yeah, I would like
answer
to
this?
answer this question. Yeah, there are lots of components I have talked about on the presentation. Yeah, we use three weather numerical weather forecaster like ECM WRF and Alaro, and all three weather forecasting system are different resolution, both temporal and also like locationally. And so, for example, we can get 3 hours. We can get from ECMWF for each 3 hours. On the other end, WRF and also Alaro in one hour, and also işte locationally, yeah, it's three of them are so different. Like ECMWF, approximately 80 kilometers square. Well, we use just we don't use the dumb scale. We use the main data for the hydrological modeling. Thank you.
Thank you. Thank you very much. There's another question about that deals with resolution. In this case, it's if you it first starts asking if you can perform the hydrodynamic flood inundation forecasting in real time, and if so, what would be the maximum area size and resolution? I don't know if you want to try to address this question.
Yeah, we have we have 5 meter resolution all over we have maps for all over the Türkiye. So the resolution is 5 meter, and we use all the maps for the hydrodynamic modeling. Yeah, it's a little bit difficult to explain because yes, some cities are too expand like Istanbul. So yeah, we are trying to yeah, sometimes we need more time because the resolution is so low here. Yeah, 5 meters it's really good to get the flood maps from the system. Yeah, sometimes it can be difficult. Yeah, it's like it's related to actually it's related to your components, your domain. Mm-hmm. And yeah, we are trying to do this shortening because time is important, you know. Thank you so much.
Thank you. Thank you so much, Salih. Now we have quite a few questions that are related to the early warning system part. So first, there's a general one on how do you reduce the uncertainty of the early warning systems? Who might want to take that?
I take the stage, and the reducing the uncertainties is quite important in this. We use the PDM, the probability distributed model, like when we calibrate the model, and we will see like how successful we are. But these are the event-based calibrations. If you have the huge rainfall happen, like in Türkiye, we calibrate the model, see like how successful it is. One of the example happened like 2 years ago. After that, we didn't have much the rainfall to see like how successful it is. But we get close to like 10 cubic meter per difference, is like over 300 cubic meter per second for flow of like one of the basins in Turkey in our the pilot project. And when event happens, we try to see how these events, specific events, can change the parameters to make us closer to the reality.
Okay, thank you. Thank you very much, Ziad. And we have quite a few questions about applying similar systems in different geographical locations. So I don't know if maybe first you would like to, in general, address that about applying if the same system and methodology could be applied to different geographical locations.
Yeah, I can say yes. And right now, as the topography and the topology is not homogeneous in Turkey, one area is like the mountainous, the other area is the flat. And we use the structure, the trend is, here is the concept. Like if you have a good concept, you can generalize this concept in Turkey. And if you want to like implement this concept in a different field, you can do that. It's all about the data. And as we say, you can forecast what you measure. If you have a dense network, data network, and you can measure some data on the field, and you can put on your system and see like how the results come out. And the important thing is here, as my friend Özgüray said, it's maybe in the future AI. Right now we don't use it in our system, but in AI terminology, you need to train the system first to see like how events can shape the reality. But if you don't have the data, enough data to train your system probably produce something, but it won't be logical or not any close to the reality.
Okay, thank you. Very, very true. So we have more questions about the real life applications of this system, which, and for example, Koth Meinutka, freelance drainage designer and director of Flood and Drainage Limited in the UK, asks if you had a chance to measure the efficiency of the early warning system in terms of saving lives and facilities in locations where you had flooding in Türkiye. And I guess you've spoken before a little bit about the testing of the system.
Yes, as Mr. Salih says that we faced only two events after our live system, and these two are very good results. One is approximately just 8%, and other one is that only 3% is close to the real life results. But as Mr. Salih says, this is a very homogeneous rain, because one of our biggest sub-basin is affected for that rain. But we have also more than maybe hundreds of hydrological models for the small and flash floods, but we didn't face any event after our live system. But we want to test our systems also for the flash floods. But for the big catchments and homogeneous rain, we can say that yes, we had a very good experience with the two big events.
Thank you. There are also some questions in terms of applying the same system and methodology to other types of disasters, so other types of hazards.
I can say right now, my colleague Salih and I working in the General Director of Water Management. And we can also, some other department also use the concept to implement drought early warning system to help the as agricultural use, or some other like the water distribution departments in some other institution. And if we have the solid and the robust network, data network, and the system as ICM, and then we put in the data, and we will have the results to see like how these result is close to in reality. But all these events can be calibrated after events happen for us. And right now, and hopefully we didn't have any much rain the last couple of years to test our system, make it much better. But if we have, hopefully we won't lose any lives or like the people's property, and to see how these events are close to our system success, or like to see how we are good at this.
And also sometimes we joke among ourselves. We will set up a drought alarm where we haven't set a flood alarm. Yes, it's not simple like that, but that's just a joke.
Thank you very much. There was also a question asking about whether the system would allow implementing layers for vulnerable places, for example, schools, hospitals, or areas where population concentrates, that kind of thing.
I can answer. Like these maps like are shown in my video, and these maps are created during flood risk management plans. And in Turkey we have 25 major river basins, and they have the different characteristics. Right now we have done this system like in 15 sub basins, but flood risk management plans were prepared for every basins. And when preparing these plans, and we will also consider like the most important places, the hospital, the schools, and the people can be like the collected or evacuated. We also put in a map to see how people can be evacuated before the flood to the safer places. And when we create a report, also we put more details as a note, say, yeah, this place is close to the school, and this taken care of well than in other places.
Okay, thank you very much, Ziad. Also, quite a few people were interested in how to incorporate considerations related to climate change into flood forecasting methodologies.
Yeah, it's a difficult question. Yeah, as you know, climate change affects unpredictable in most time. But in my opinion, the flood forecasting studies will not be affected negatively due to long-term effects of climate change. I mean, long-term effects, because we can calibrate our hydrological models again according to the new situations. However, the problem here is the change in rainfall regimes. It can be a problem for heavy precipitation occurs suddenly. It can be difficult sometimes to predict these really sudden heavy rains. And these in particular cause flash floods, For this reason, the radar rainfall data, which provides also spatial data, is so important. We need to improve weather radar navcasting. I said navcasting, not forecasting. This helps us a lot. Thank you.
Thank you. Thank you very much, Salih. Okay, continuing with data, this time historical data for the system. It's a question from David Clark, Senior Professional Technical Officer for Department of Infrastructure in the UK. And he asks, how far back does your historical data go, and how do you integrate this historical flood data into your model outputs as portrayed in the ICM models?
Yeah, we use hourly data for the flow and also rain, and not daily, because if you use daily data for the flow, also rain, yeah, you can not see the peak flow most of time. So you should use hourly data. And in this project, we use 6 years data for all for preparing all the hydrological modeling. Thank you.
Thank you very much. And okay, so we continue having a lot of questions. There's a lot of interest in this issue. So this question is from Miguel Santos, design civil engineer at Agencia Portuguesa do Ambiente in Portugal. And the question is, in relation to predictive activities, how many precipitations models are used to forecast runoff? Let me read the whole thing and see if you can decide who will answer after. It says, if there are significant discrepancies between the 2 or 3 precipitation models used for prediction, the results can influence public opinion regarding the effectiveness of this model. It's important to know that the primary issue to address remains the prediction of precipitation, not the hydrological and hydraulic models themselves. That's what this person's opinion is. So the question at the end is whether the public in Turkey has been educated to understand the complexities involved in these predictions. So this it's a little bit beyond the model itself, but how this model will be used. So I don't know if you want to reflect on this.
Yeah, we use 3 weather forecasting. Yeah, you are true. But it is just for us, not for public. Yeah, we are here for this because we are investigate the forecasting comes from meteorological service, Turkish meteorological service, ICMWF, WRF, and also Alaro. And also sometimes we use radar rainfall. And after analyzing with our colleague here, there are lots of experts here. After analyzing the events, the forecast, yeah, if we need to prepare a report to warn to the public, yeah, it should be very short and very basic to understand to public. Yeah, you're right. Yeah, it should be very short and basic, but it's all just for us, not for the public. Thank you.
Thank you. Yeah, so at the moment, it's the system is predicting the information for a government organizations. I understand, right? Because there is another question that is a little bit related, I think, which is it asks about managing liability in cases where there would be a flood warning when there isn't an actual flood after, or vice versa. When there is no flood warning yet a flood occurs. So I don't know if you would like to speak about how to handle this part of the whole prediction and early warning, not just sort of the technology in the system, but how it's going to be taken by the public?
The structure actually is pretty simple, and yeah, we collect the data from the different institute, and we manage the data, convey the different knowledge here, and like broader expand our horizon, like how it will change the situation after data comes in. And when we manage data here and create an alarm and the warning needs to be published if we decide, and we tell the relevant institution it's working under the Ministry of Interior. We call it emergency presidential. We call it AFAD, is a Turkish acronym. And all the AFAD is responsible for all natural disasters in Türkiye. There's an earthquake, landslides, and the flood, and some other hazards as well. And when we give a warning, we tell the AFAD first, and they have also system information system application, also web interface. Like when we integrated their system, when we create an alarm, they will get it directly and tell the locally, and our like in whole business in Turkey, like if it happens like everywhere, it's not possible. Maybe like if it happens, it's like I don't know what comes next. And mostly locally by like the text messages and emails for the relevant institution, and some like applications and like the social media. These are 3-4 the way we can connect, or the AFAD can connect to the people like in the specific region before flood happens.
Thank you, Cihat. Thank you for...
Maybe I can add something. Top level systems like TATUS must be aligned with the social and cultural context of the project location, and also must ensure effective collaboration among authorities, and that must be aligned with also the public policy. It must be different absolutely in the Turkey governmental, and it must be different for our government. But you have to mix all the your suitable prediction methods, and also with the align with your social and cultural context of your city or your country.
Thank you, Huray. That's so important, like you say, aligning the system with the cultural and regional context where you're operating. Because a lot of questions have asked about other geographies and exporting your model. And I would like to ask you just a general question about flood forecasting, and if you would like to reflect on this extremely important field where you're working, and what we'll be able to see in the future, not very far away in the future, more like a near and midterm. If you would like to reflect on that, where do you see things going in the next 5 to 10 years?
I think AI comes and we all go home and just to wait like what AI can do. see like how successful it is. Like every day, like we are seeing the videos, like how AI predicted this event, or how AI predicted the tsunami or other natural hazards. But that's not possible in the near future. Right now, every system needs a human to run these models and to think how you can make much better. Right now, the team we are working in right now is open to expand the more and more, and every day we learn each other, and we checked how the world responds such events, and we are reading articles, like checking the news and talking to other people like in the different institutions and different countries, and we are going visit their institution. They are coming here to see how we can improve our system. And when they comes here, and we will collect all these ideas and define, like, see, okay, we can test these and see how the system reacts and make it more logical. And these are here like the foreseen near future for me and for my friends as well, if I say in their behalf.
And I think I'm agree with all of your sentence with Mr. Cihat, and I think we cannot prevent so many disasters. We will face with it, but I believe, like Mr. Cihat, that eventually these systems will become much more successful, and we will find the ways to navigate through disaster with much less damage, but we will face it. Eventually, sooner or later, it depends on your country, your maybe financial situation, but in near future, we will find the ways to navigate through disaster with much less damage.
Thank you. Sorry.
Yeah, last sentence for me. Yeah, weather forecasting is so important, I think, because both hydrology and hydrodynamic modeling are more constant, but we should improve our weather forecasting. We should especially use radar rainfall. And second one is data. Data is so important. Yeah, everyone needs data to forecast the floods. Both, if you prepare some hydrological modeling, or AI predict the flood. Yeah, everyone needs good data and data network. Yeah, if we can forecast good, weather forecasting, and if we have good network, data network, if we have, we can predict, we can forecast floods. Thank you.
Thank you very much. Thank you to the three of you. And so true. We end on that note. We cannot prevent extreme weather events from happening to certain extents, but we can be prepared for them. So the importance of flood forecasting and early warning systems just cannot be emphasized enough. And we highlight the importance of data. And we have the advanced technologies to make this system a reality, like we have seen today, and to see them play a crucial role in mitigating the devastating impacts of floods, so we can move from crisis management to flood risk management, as we have seen today. I would like to thank the speakers for this discussion, and we'll close this session. They will be able to see and answer any remaining questions in the chat. And I would like to remind you that you will be able to access the recorded event on the website of Smart Water Magazine. You're also going to see a brief survey on your screen about the topic of the webinar and whether you would like to have more information on it. Thank you very much for joining us today, and we look forward to your participation in future webinars of the Autodesk Water webinar series.